Good day, Professor Hasley and Mr. Kama. My name is Choong Jun Jie from BMMD. Now I will present my final year project with the title of Simulation of Synthetic and Natural Rubber Compression-Deflection. These are the contents for the presentation. It includes research background, problem statement, objective, scope, literature review, methodology, conclusion, and project potential. The first part is research background. Rubber is one of the most commonly used material in Malaysia due to its properties. One of the rubber's properties is elasticity. There are two types of rubber, which are synthetic rubber and natural rubber. Rubber's quality are based on degree of vulcanization, which is the number of chemical cross-links formed between the molecules of the chain. N6 is a platform that develops markets and support engineering simulation software that used to predict how product design will behave in real world. Problem statement. There are a few techniques used to detect the degree of vulcanization of rubber compound, like the dynamic mechanical analysis or the Moore's viscosity test, but we are lack of understanding on the difference of stress strain profile between polypropylene rubber and natural rubber under the FSTM D575 standards. In real world, lot of sample testing is required to obtain an accurate result, and that is why simulation is crucial before the real experiment is conducted to save cost and time. Also, the simulation provides safe way to test and can be used to explore on how material behave under various situations. There are two objectives in this project. The first objective is to simulate compression test model of vulcanized polypropylene rubber using ANSYS 2020, R2, and ANSYS Mechanical. The second objective is to analyze the difference on the stress strain profile between polypropylene rubber and natural rubber. The scope of this project starts with constructing 2D axisymmetric model of the rubber specimen. Then the compression test parameter will be defined before the compression test simulation of CR and NR using ANSYS Mechanical. After the simulation is completed, both CR and NR results will be generated and analyzed. The next part is literature review.
Polypropylene rubber is a diene-based rubber. The 1,4-polypropylene is commercial grades are mostly transproduced by free radical emulsion polymerization of 2-chloro-1,3-butadiene as shown in Figure 1. CR typically display a high resistance to ozone plating, aging heat, chemical attacks. Its resistance to flames is remarkable, yet polypropylene is one of the few rubber that are self-extinguished. Natural rubber is the only non-synthetic rubber that is commonly used. In its backbone chain, NR is predominantly composed of cis-1,4-polyisoprene as shown in the 2. The main product of natural rubber includes tires, conveyor belts, vibration isolators, tabs, hoses, and tubing. It is often used to score other synthetic rubber for their strength, elasticity, and spherical properties as a guide. Figure 1 is the mechanical properties of CR and NR, where it covers the hardness range, maximum elongation, compression set, creep, and elasticity. Moving on to the strain measurement of rubber under compression loading. The rubber stress strain graph in Figure 3 shows that when the load is increased, the behavior as the load is removed is not as sad as that. You can refer to Figure 3 that this curved loop is known as hysteresis. According to Chai, the deformation of rubber is considered as a large deformation. Therefore, there is a need to have the material uniaxial compression, biaxial compression, plane compression, stress and strain parameters for investigation. Even with the same material, if the hardness is not the same, for a higher hardness of material, the deformation resistance is also bigger. This part is axisymmetric approach. In 2D, an axisymmetry is that an axis or a line can be drawn and the picture is mirrored across that axis or line. Shown in Figure 4, in 3D, an axisymmetry is that it is possible to draw a shape into a plane and round it around an axis. The specimen used in the simulation happens to be a cylindrical shape, which meets the requirements of axisymmetric, so it is assumed to be axisymmetric. This ASTM is a standard test method for rubber properties in compression deflection. In this standard, there are test method A and test method B. Test method B is a compression test of specified force, which means it is a test to determine the deflection after specific compressive force is placed on the specimen. Table 2 shows the experiment parameter used in test method B, where it includes the shape, thickness, and diameter of the specimen, the displacement, and the loading direction. ANSYS Workbench is the framework on which the broadest and deepest suite of advanced simulation technology. ANSYS spaceclamp is a model that has been imported or produced in spaceclamp and be submitted with this add-in to ANSYS Workbench. ANSYS Mechanical is the flagship of mechanical engineering software system that uses finite element analysis with its interface for structural analysis. The next part is methodology. This is the flowchart process of this project, where it is started from constructing 2D axisymmetric model to analyze the result. In the simulation, there are mainly three parts. First is construct 2D axisymmetric model in ANSYS spaceclamp. Second is to define the experiment parameters in ANSYS Mechanical. And the last part is simulation and generate the result in ANSYS Mechanical. To construct a 2D axisymmetric model, we first create a static structural project on ANSYS Workbench. We double-click on the geometry to launch ANSYS spaceclamp. After that, we choose the plane that we desire to sketch on. So in this case, we choose y-axis plane. Then we choose rectangle, and then we sketch it on the origin with a dimension of 14.3 millimeters and 12.5 millimeters. After that, we end the sketch. Then we can save it to the desired location. Define the experiment parameter and simulation to make sure the geometry is in 2D. Then we double click on the model to launch ANSYS Mechanical. First step we do is to make sure the geometry is axisymmetric. Then we assign the specimen to a material. In this case, we choose thin rubber, which is corroded rubber. Then we right click on the sample structure and we choose quick sample. Insert it and apply it at the bottom of the specimen. And we right click on the sample structure again and choose displacement and apply it on the top of the specimen with x equal to 0 and y equal to negative 2.5 millimeters. After that, we go to the analysis setting. Then we set the step at time to 2.5. And we turn on the auto time stepping and also turn on the large deflection. After that, we set all the subsets to 100. Then we right click the solution and insert the result that we want to generate. In this case, we want the normal stress and a normal strain. After you choose, right click on the solution and click stop to run the simulation. After the simulation is completed, the result will be shown as shown in the video. And on the software, you can play the animation when you see when the compression applied on the specimen. The right corner is the tabular data of the result. We can right click it and export it as an Excel file so we can analyze based on the result.
Next part are result and discussion. For the compression test simulation parameter, this is the data value of initial shear modulus and incompressibility parameter for both CR and NR. The value can be referred in Figure 5 and Figure 6. The next parameter is displacement. Displacement is applied on the top of the model and the displacement value is set to negative 2.5 mm in y-axis to represent the decrease in thickness of the specimen. The fixed support is applied on the bottom of the specimen. Figure 7 is the analysis setting, 2.5 seconds of step and time where 1 second represents 1 millimeters of compression and 100 substeps are act as a ramps, which means the stress strain result is corrected every 0.025 seconds until the time is 2.5 seconds. Figure X shows the schematic diagram of compression test. Moving on to the normal stress result, from the power control plot in figure 9 and figure 10, we can see that the NR has larger red region and also the larger maximum stress value as compared to CR. The controls outer edge of NR have distributed with lesser stress as compared to CR. This is due to the hardness of NR is higher than CR. This is the graph of normal stress versus loading time. According to the result as shown in figure 11, NR has the higher minimum, average, and maximum normal stress value than CR. NR has the maximum tensile strength of 4,500 psi, while CR has only 4,000 psi. This means that the NR can withstand higher stress than CR while being stretched before cracking. The result of CR and NR's normal stress from the simulation is tallied with their mechanical properties. This is the result of normal elastic strength. From figure 12 and figure 13, we can see that both color control plots have relatively small area of red region. The red region area is on the top and bottom right for both color control plots, where the maximum strain is on. For the result, we can see that the NR has a larger change in dimensions than CR after the compression is 5. This is the graph of normal elastic strain versus loading time. According to the result as shown in figure 14, NR has the higher minimum and maximum normal elastic strain value than CR, but CR has slightly higher average normal elastic strain value than NR. NR has the maximum elongation of 650% and CR has only 600%. This indicates that the NR can be stretched longer than CR by 50%. The result of the CR and NR's normal elastic strain from the simulation is also tallied with their mechanical properties. Figure 15 is the average stress strain graph obtained from the results. The larger the stress, the larger the strain. The gradient of the stress strain graph is called elastic modulus. You can see from the graph that the elastic modulus of NR is much higher than CR. According to Nunn, the hardness of a material can be characterized by the area underneath the stress strain curve or the value of elastic modulus. The larger the modulus, the harder the material. So we can say that the NR is harder than CR based on these results. In conclusion, both objectives of the thesis have been successfully achieved. The simulation of compression tests have successfully conducted using MSys software. Overall, the NR has a higher compressive and tensile of both stress and strain as compared to CR. And the last is the stress strain results are tallied with their mechanical properties, where NR has higher maximum tensile strength and maximum elongation than CR. The project potential is the study finding could be applied on all the industry that involved with rubber products. This helps industry to identify which rubber is suitable for its product based on the stress strain results. The cost is different for each rubber. Industry should consider other characteristics besides tensile strength and elongation. Thank you very much for your time, and that is all for my presentation.